Okay guys, so yesterday we were discussing magnetic effects of current, where we discussed that whenever current flows in conductors, it generates its magnetic field, and that magnetic field can be evaluated with the help of the Biot-Savart law, and we evaluated it in case of infinite conductors, and the expression that we got was mu naught I upon, yes, the expression for the infinite conductor, it was mu naught I upon 2 pi r, right? And then I asked you for a homework. The homework was this: if the current is flowing in a circular loop, what is the value of the magnetic field generated by this loop? Did anyone do it at home? No? Too busy selling your business? Yes, Maya, did you do it? Why? He has a different work. He sells sleeping. Okay, see. Now, when we talk about circular loops, okay, if current is flowing like this, the radius of this loop is r, okay, and you want to evaluate the magnetic field, important, very important. Then the expression for the magnetic field inside the loop at the center, very important. The magnetic field at the center of the loop is given by mu naught times the current, again the same thing that we discussed yesterday, but divided by 2 times r. So there is no pi in the denominator. This is the expression. Is that fine? Now, if someone tells me, sir, how do we evaluate the direction of the magnetic field? So we have to understand the direction, okay? What is the direction of the magnetic field at point O? So how we do that? We already yesterday have studied this rule, the right hand rule, right? So we will apply the right hand rule here as well. How? See, if we talk about this loop, the current at this end is flowing like this, and when the current reaches here, it is flowing like this, correct? So if I try to show you the direction of the magnetic field, can you tell me for this conductor here, the current is up? And to evaluate the magnetic field here, see, fingers are going in, isn't it? Therefore, the magnetic field at point O is cross. Is it? Is it? And at the same, cross means inwards. Is that fine? And if you evaluate with the help of this side, so current is flowing down, and you curl the fingers and they are again going in. So the magnetic field here is inwards. Is that clear? Is that clear?
Yes.
This is the concept. Now, if the current was flowing in the reverse order, that means in that case it was clockwise. What if the current was flowing anti-clockwise? Counterclockwise. So again, if you tell me if the radius is r and the center is at O, what is the magnetic field? The magnetic field is again mu naught I upon 2r. Is that fine? Is that fine? But if you have to evaluate the direction, how do you evaluate the direction now? Can you tell me? What will be the direction of the magnetic field? So the current is flowing like this, and it is flowing like this. So what we do? Yes? Huh? Same thing again, yes? So the current here, it is going up, and you go towards the point of analysis. Now try to curl your fingers. When you curl your fingers are coming out. That means it is dot. Is that fine? Is that fine? Similarly here, your hand will go like this, isn't it? And when you curl it, it's coming out. Therefore, it is dot. Is that clear? So magnetic field, direction, magnitude, this is the magnitude, and you know the direction as well. So, in order to find the direction in case of circular loops, I will give you one better method to find the direction. The direction can be found by this method, see? If the current is flowing in clockwise direction, for example, then the right hand rule that you have already studied has to be used in the reverse order. Reverse means, what was this in the right hand rule? The current, and this was the direction, right? Now, for circular loop, this is the direction, and this will give you the magnetic field. It's reversed. So the current, curl your fingers along the direction of current, like this. Where is the thumb going? Inwards, khalas, inwards is cross.
So, this is wrong.
No, it's correct. Isn't it same? Understood? So when you are talking about the circular loop, you can use the right hand rule as we have discussed, but in order to see, we have to again check, do this and that. Better is to use the right hand rule, but in a different way. The way is this: curl your fingers along the direction of current. Okay? The thumb will give you the direction of the magnetic field. So when you curl your fingers along the direction of the current, when you are finding the direction of the thumb is pointing inwards, therefore it is cross. Is that fine? Similarly, if the current is flowing in the anti-clockwise direction, what will happen? So you will curl your fingers like this, isn't it? Thumb is going up, khalas, this is the same. Is it clear? Is this clear? Now, when I take the analogy here, very important. I have discussed it with you. I'll still try to explain it to you. Like for example, we have a bar magnet, the north pole and the south pole. We know the direction of the magnetic field lines, do we? Yes? So tell me, magnetic field lines start from north and they terminate at? Isn't it? And inside they are from south to north, right? We know this. Now if you talk about a loop, current is flowing in the clockwise direction, and when you apply the rule, as for you, the magnetic field is inwards, so it is cross, right?
Yeah.
Correct? For a person, for you guys, we are looking at the loop from this side. But there can be another person who is looking at the loop from the other side, isn't it? For you, the magnetic field lines are going in. Can you tell me into which pole do the magnetic field lines terminate? Yes? They terminate at the south pole, right? So they are entering, magnetic field lines enter the south pole, right? And here again you are seeing that the magnetic field line is entering, right? Therefore, when current flows in the clockwise direction, the loop behaves as the south pole. That is the reason that we have discussed. Is that fine? Similarly, when your current is flowing in the counterclockwise direction, what is the direction of the magnetic field? Yes? It's out. So it is like this. So the magnetic field lines are coming out. So the magnetic field lines come out from north pole. Therefore, this behaves as a north pole. Is that clear? Is that clear? Now, very important thing. When you talk about a loop, if you are looking at the loop, for you the current is clockwise, isn't it? But for a person who is on the other side, for him, the current is counterclockwise, isn't it? If for you, what is this for you? What is this direction for you? Clock, but for me it is anti-clockwise, isn't it? So that means for you, if it is south, for me it will be north. Therefore, again, the same thing that we discussed yesterday. That north and south are always together. They are not in isolation. We cannot have them in isolation. Is this clear? Okay? This is the concept of the magnetic field lines in case of a circular loop. Fine? Okay, now let us come to the next topic, and that is the case of the superposition. And there is a numerical. There is a figure in which we have two straight conductors, okay? Current is flowing like this. This is current I1, and then in this the current is I2, fine? The distance between the plates, between the wires, is 2 times A, okay? So, where A is 30 centimeters, so A is 30 centimeters, and the question is, the currents are 20 amperes and 30 amperes, so this is 20 ampere current, and this is 30 amperes of current, fine? And the currents are flowing in the opposites. The question is, find the magnitude and the direction of the magnetic field at a point P at the center of the two wires. So, the distance is 2A, we have a point here, point P, which is at the center. That means this will be A, this will also be A. Is that fine? The question is, what is the magnitude and the direction of the magnetic field at point P? Yes. Tell me. This is an infinite conductor. This is also an infinite. How do you find it? We know the expression. What is the expression for the infinite conductor? Yes? Mu naught I upon 2 pi r, right? So we have to find the direction and the magnitude due to the first. We have to find the magnitude and the direction due to second. Then we can find the total. And you can give me the direction as well. Come on, do it. Do this question. Come on. Yes, Talvi. Right. Mu 4 pi 10 to the power negative 7. Yes, sir, we do it. No homework, no homework. Salam Faisal. पढ़ाई करोगे तुम कि नहीं? Yeah. I don't know. You have to check. First of all, find the individual values, then check the direction. Okay. Yeah, R will be exactly. Yeah, A is 30 centimeters. Very important. We have to find the magnitude and the direction of the magnetic field. So, first of all, you know, there are two conductors, therefore there will be two magnetic fields. One will be due to this, another will be due to this. So, find the value individually and then add or subtract them. That is due to one. Due to second? 2 by 30,000. 30 centimeters. What? You have to find the net value and the direction as well. What is the magnitude and the direction? So 20 ampere here, 30 ampere here. This is A, this is also A. Come on, tell me, how do you evaluate this question? Yes, Talveed, any idea? Still any suggestion? Yes, Aisha? Tell me. First we evaluate the magnetic field due to the first conductor, okay? For the first conductor, the magnetic field at point P will be given by mu naught times the current upon 2 pi times the distance, isn't it? Yes? So what are the values? Values are mu naught is 4 pi 10 to the power negative 7. What is the current? Current is given, it is already 20 amperes, right? Upon, yes, 2 times pi times the distance. Now the distance is A. And what is A? 0.3. Exactly, 0.3. Fine, khalas. So this and this goes 2 and 2 will cancel. Oh, sorry, 2 and 2, not 4. 4 is still here. So this will be 10 and this will be another 10. So it will be 10 raised to the power minus 5. So it will be 4 upon 3, 1.33 into the 10 to the power negative 5. Yes?
Yes.
So it is 1.3 in multi times 10 to the power negative 5 Tesla. This is the magnetic field due to the first. But can you tell me the direction? Direction of the magnetic field created by the first. Yes. What is the direction of the magnetic field generated by the first? So what you do? Current like this, go towards the point of analysis and then curve it. So it is in, exactly. So it is in. This is the magnetic field. It is inwards. Is that fine? Now we find the magnetic field due to the second. Similarly, so the magnetic field due to the second would be, yes, 4 pi 10 to the power negative 7 times the current. Current is 30, right? Upon 2 pi times distance is 0.3. Is that fine? Again, the same thing will happen. This will be 2 here. This will be 31R, 300R. So it is 2 times 10 to the power negative 5 Tesla. Is that fine? This is the magnetic field due to second. Can you tell me the direction? Yes, this time the current is like this. How is it out? Same. Understood? Please understand, thumb is along the direction of the current. So you place the thumb along the direction of current, it's going in. Therefore, both the magnetic fields are inwards. How do you find the total? You add them, khalas. Because the direction is same. If the direction was different, then you had to subtract them. Is it clear? Okay. So the total magnetic field would be 1.3 and 2. That is 3.3 times 10 to the power negative 5 Tesla, and all the magnetic field is inwards. Khalas, this is it. Any doubt? Clear? Very good. Fine? Okay. This is the same solution. Okay. The same thing. Okay, now come on, do this question. Same question, just that the current is flowing in the same direction. I1 equal to 20 and I2 equal to 30 amperes. The point is here, point P. This will be A. This will also be A. Same question. Tell me what will be the net magnetic field here? In or out? Will the value of the magnetic field change? Will the magnitude of the magnetic field change for first and second? The values are same. So B1 again would be 1.3 times 10 to the power negative 5 Tesla. But what will be the direction? No. Current is like this, so it is in. Is that fine? What is the magnetic field due to second? The value will again be the same, fine? Because the current is same, the distance is same. The magnitude will be same. 2 times 10 to the power negative 5. But what is the direction? Yeah, this is important. Now see, it is outwards. Fine? Now we have two magnetic fields, but they are in opposite directions. Therefore, the net magnetic field will be evaluated by, yes, which magnetic field is more? The second one, right? Therefore, we are seeing that it will be B2 minus B1. Is that clear? Is that clear? So that means 2 minus 1.3. Answer would be 0.7 times 10 to the power negative 5 Tesla. Can you tell me the direction of the net magnetic field? Exactly. It will be outwards. Because more out, less in. Therefore, overall, the answer will be out. Is that fine? So this will be the answer, but outwards. Clear? See the difference. Just that current's reverse, magnetic field is only 0.7. Previous case 3.3. Understand? Is that fine? Okay. Copy this as well. Salama Faisal is already sleeping. It's good. Fatima might be ordering something from Talabat. Clear? Now before I go to the solenoid, one more question. I'll write down the question. A current of 7 amperes flows in a coil of radius 4 centimeters in clockwise direction. Okay, find the magnitude and direction of magnetic field if the coil is in XY plane. Come on, do this question. Do this question. Then we have one more question. Two coils are shown. Come on, do this question. The first one and the second one. The first one you did? Yeah, tell me the answer.
3.5.
15?
I got 3.5.
3 point?
Multiplied by 10
10 to the power?
-5.
Direction? What about the direction? It is in the XY plane. XY plane is if this is the X axis, this is the Y axis. What will be the direction of the magnetic field? It will be inwards, but along which direction? If it is in XY plane, then it should be in the coil is here. This is the coil. in X and Y plane. Inwards means it will be along which axis? Z axis. Isn't it? When you place, say for example, there is a coil, see? This is the coil. The magnetic field is in, so it is along which axis? The Z axis. Isn't it? Yes, anyone else who got the same value?
I got the same problem.
3.5 times.
You got here 6?
Negative 6.
I got
Negative 5? So current is 7 amperes, radius is 4 centimeters, that means 0.04 you have to use. Yeah, that is a problem. So the magnetic field would be 3.5 and it would be along, it will be in across because it is inwards, fine. But if you have to say along which axis, very important. So X and Y, therefore it will be along Z axis and it is inwards. So it would be along negative K, if you remember what are the unit vectors along these directions. You remember? See? This is the I, this is J, and this is what? Fine? Now these are the positive directions. Now when you are talking about inwards, that means you are talking about this, so it will be negative K. Down would be negative J and left would be negative I, isn't it? The unit vectors along these directions. You know something about them? No?
J, K.
No, you don't know? Okay, listen. These I, J, K, they are called as unit vectors. What are they? They are used to give directions. You don't write along x-axis. You just write I, it means it is along x-axis. Is that fine? Yes? Wrong?
Yeah.
What did you get?
1.099 times 10 to the power minus.
What expression did you use? 7 and 4. The expression that you had to use was magnetic field is equal to mu naught times the current upon 2R. So it is 4 pi 10 to the power negative 7. Current is 7 upon 2 times radius is 0.04.
I did 2 pi, that's to do with the axis.
You used pi?
No,
Yeah.
yes.
Yes.
I didn't use it.
Then how did you get the same value?
Mistake, I didn't put the pi in fourth. They did 4 times 10 to the power negative 7.
Stop.
4 pi 10 to the power negative 7 times 7 upon 2. This pi, delete this pi. There is no pi in the denominator. Aisha, what did you do?
I got 1.0. Yeah, 1.0.
Yeah, see, 1.09. Good, Fatima Talal. So it is 1.099 times 10 to the power negative 4 Tesla. Oh my God. See what value did you tell me? This is not the value. Incorrect. Because you are using a wrong expression. This is a circular loop. There is no pi in the denominator. That's what I told you in the beginning. Is that fine?
Yes.
Okay, now please do this question. You have two loops. They are coaxial. Very important. This is the common axis. So they are coaxial. Okay. Both have the same radius. Both have the same value of current. But the current has an opposite direction. If there are two loops, see, I'm trying to show you the three-dimensional thing. One loop is this, the other is this. Okay, but if the current here is clockwise, then in this loop the current is counterclockwise. The question is, what is the magnetic field here? They are very close. They are very close. You don't think that they are separated. They are very close, like this. So, what is the magnetic field at the center? That is the question.
Check the direction and then up.
You have to see, if you add or subtract, first you have to think about that.
Find the direction.
Yeah?
Should find the direction.
How do you find the direction? Yes?
Both of them are north.
So see, there are, this is the coaxial case. Fine. The centers lie on the same axis. So there are two loops. One is this, and the other one, it is not this far, it is very close, okay? It's very close. So for this, the current is, if the current is flowing in clockwise, for this, the current is counterclockwise. Fine. The value of the current is same. The radius of the coils is same. So if you want to find the magnetic field due to one of them, it would be mu naught times the current upon 2R. Is that fine? For the other, it would be again the same. You just have to check whether, what is the direction? What is the direction? So let us try to find the direction. Yes? Inward for both? Let us see. Let us see. When we talk about the magnetic field, which is to be calculated for the point, which is say somewhere here. That means we have two coils. Understand this from the concept. You have two coils, and the point is here. Okay, you have two coils like this, and the point to be evaluated is somewhere here. Fine. Now, in this coil, the direction of the magnetic field is like this, isn't it? If the current is flowing in the counterclockwise direction, the direction of the magnetic field is this. But for this coil, because the current will be in clockwise direction, it will again be in the same direction, isn't it? Therefore, we have to add it. We don't have to subtract it. Clear? See, for this coil, it is like this. Imagine the coils in 3D. This coil is like this, the first one. This is the first one. And this is the second one, okay? Now for the first one, the magnetic field lines will go like this, isn't it? So for the first one, magnetic field is this. Clear? Fine? But for the second, yeah, the magnetic field is here. Okay, in this case, we are having the opposite colors. Therefore, what will be the net magnetic field?
Minus.
It will be 0. Because the individual values are same. Mu naught I, current is same, divided by 2 times radius. Radius is same, therefore the magnetic field will be same. B1 in magnitude will be equal to B2. But we are seeing that because they are in opposite directions, we have to subtract them, and the answer would be what? 0. We don't need to evaluate it. If the direction of the current was same, then we have to add them, yes. Then the answer would have been mu naught I upon R. Is that fine? This is the concept. Clear? Any doubt in this? Okay, now let us come to another important thing. That is the case of the solenoid. Now we have already discussed in electromagnetic induction what is solenoid. So you already know that when we wound a coil into helical form, we form something called as the solenoid. Fine. Now here we have a coil, and this coil has been wound in the form of a helix. Okay, and this coil forms a solenoid. Fine. Now when you talk about the solenoid, say for example the length of the solenoid is L. Okay, and the number of turns is N. It has N number of turns. Fine. Then I have already told you, because the loop behaves as a north pole or a south pole, in this case, because the current, see the direction of the current, very important. Current is flowing in this direction. Current is flowing in this direction, coming out in this way. So that means when current is flowing, it is clockwise, right? Clockwise means which pole? South pole, isn't it? So therefore this is south, and therefore automatically this will be north. And the magnetic field lines run from north to south. So the magnetic field lines go from north to south. Is that fine? And inwards, inside the magnet, inside the solenoid, the magnetic field lines run from south to north. Is that fine? Now what you are seeing is the magnetic field lines are very close inside, and they are very far away outside. So that means outside we have a weak magnetic field, and inside the magnetic field is very strong. Is that fine? Now if someone tells you what is the value of the magnetic field in case of a solenoid, I think I have already shown you the expression. The expression is this. It is mu naught times small n times current. Khalas. Mu naught times small n times current.
This is for solenoid.
Yeah, for the solenoid. Fine. What is the small n? Small n is this total number of turns upon length. And this is simply the turn density. Okay? Whatever the density is, number of turns per unit length. And if you have to find the direction, I have already given you the direction. From now, north to south. Is that fine? Now, what is one of the beautiful things is that, yes?
What's that?
N is the turn density. Okay? One of the beautiful things is that you can reverse the polarity. Why? Because when you change the direction of the current, the polarity will be reversed. Isn't it? If you want to increase number of turns, magnetic field will increase. If you want to decrease the number of turns, magnetic field will decrease. So it depends on you what kind of a magnetic field do you want to generate, and you can do that with the help of a solenoid. Is that fine? So remember, magnetic field inside is calculated, not the outside one, because the outside one is not uniform. The field lines are not at a constant distance. See, the distance is less, it is increasing maximum and then again decreasing. Fine. So we do not evaluate the magnetic field outside, we evaluate the magnetic field inside only, because the magnetic field which is inside, this is the inside magnetic field, okay? This magnetic field is uniform, that is why we evaluate this. Uniform means it is the same everywhere, therefore we have the value. But for this, the value is different at every point, therefore we do not evaluate it. Is that fine? Clear? So there are some points regarding this solenoid. The magnetic field is uniform inside, okay, very important. One end of the coil acts as the north and therefore the other one will act as the south. It depends on what is the direction of the current, fine. And magnetic field is stronger near the ends. Why? Why is it stronger near the ends? Because the coil has very close magnetic field lines there. When the number of turns, when the lines are very close, strength is high. When the lines are far away, strength is less. So it is one of the points. Is that fine? Clear? Okay. And one important thing, if you increase the value of the current, you can change the magnetic field. If you change the turn density, it can again change the magnetic field. And one important thing, very important thing, if sometimes what happens is that we introduce a material, a solid iron core, okay, solid iron core inside, okay, which is ferromagnetic. Okay. Now this material increases its strength. Why? Because ferromagnetic substances are those substances which attract the magnetic field lines. So they do not let the magnetic field lines to go wasted. They keep it within, due to which the strength of this solenoid increases. Is that fine? So that is why we introduce what? A ferromagnetic material. Ferromagnetic is a ferro means it allows the magnetic things. So the magnetic field, it is retained within. It doesn't get wasted. Is that fine? Whatever magnetic field is generated, it's not wasted. Maximum 99.9% of the field lines are retained by the solenoid, and therefore it behaves as a very good magnet. Is that clear? Okay.
Can you go
Back. So see, this magnetic field can be changed by changing the current or changing the turn density. It depends on you. If you increase the current, magnetic field increases. If you decrease the current, this decreases. If you increase the number of turns, it increases. If you decrease it, it also decreases. Is that fine? That is the concept. Fine. So then we have this, the expression. Okay, the definition may be it is wrapped into many terms, that is, you simply have a helical form. And I told you magnetic field is given by this expression. What is n? It is the number of turns upon the length. And the direction is determined by the right hand rule, which you already know. That one of the poles behaves as north, the other behaves as south, and therefore you can find that. Is that clear? Now do this question and I will stop with this question. There is a superconducting magnet in the form of a solenoid, very important, of length. So length is given and can generate a magnetic field of 9 Tesla. So the magnetic field is also given. When carries a current of, so the current is also given. Find the number of turns in the solenoid. We have to find the number of turns in the solenoid. Try to solve this question. Come on.
What the solenoid is the Ni?
No, it is mu naught times small ni. Very important. He is asking us to find the number of turns. He is not asking us to find the turn density.
Formula for the thumbs that n equals.
You know, small n is equal to what? Capital N upon L.
What's capital N?
Total number of turns upon the length. Yes? So try to use this expression, and this is where I stop.
What is n?
This is the turn density. Turn density, number of turns per unit length. You have the length, you have the magnetic field, you have the current. So you have current, you have the length. So you can replace this expression as,
I have B.
yes. So you have to find capital N. 47,000? How did you find that? Okay, let me try. Magnetic field is how much? 9 Tesla. Mu naught, it is 4 pi 10 to the power negative 7. Times n we have to find. Current is 75 amperes upon length. What is the length? 0.5 meters. Is that fine? So which implies n is equal to, solve this equation, come on.
You want the capital N or the small?
No, see, understand the question. The question is, find the number of turns. If he was asking number of turns per unit length, then we have to find small. If he was asking us to find the turn density, then we have to find small. But he is asking us to find the number of turns. Number of turns means total number of turns. Fine? Yes, Nagleen, what is the result? You evaluated this? Yeah. So it is 9 times 0.5 upon 4 pi times 7 times 10 to the power 7. Yes, give me the value. 4.5, so this is 40?
No.
What is it?
47,700.
47,700?
46.
46?
Yeah.
It is 75 amperes, right? Anyone else who want the same value? 47,746, right?
Yes.
Yes, 47,746 is the correct choice. Is that clear? So this is where I stop, and inshallah maybe tomorrow we will discuss. Take this question as homework. 1000 turns distributed over a length, so you need to understand whatever is given. Try to solve it here. You have to understand what is given. You have to see what is given. So what is given in the question?
Magnitude.
See, what is this? The magnetic field? 1 into 10 to the power negative 4 Tesla.
We have N.
We have capital N, very good.
And then the lowercase n as well.
No, we have the length. Yeah, 0.4 meters. Okay. The question is, what is the current required in the winding for this to occur? So we need the current. Is that fine? The same expression again? The same expression will give me magnetic field is equal to mu naught times n times I, right? So we have to find I. I would be given by B upon mu naught times small n. Yes? Isn't it? So we just put in the values. What is the value of magnetic field, Hiba? What is the value of the magnetic field? It is 1 times 10 to the power upon mu naught, you know, 4 pi 10 to the power, and then n. What is small n? It is capital N upon small n. Is that fine? So we can find small n like this. It is capital N upon L, and capital N is 1000, so it is 1000 upon 0.4. How much is this, first of all? 1000. 1000 upon 0.4? 2500. So just put in the value 2500 here. Khalas. We found the current.
I got small.
0. 0.0032?
0.02.
No, I don't think, because it will be 1000. Yeah, it will be. Yeah.
0.032 or 318.
Anyone else who got the same value?
Yeah.
You got the same value? You got the same value. Okay, yeah, this is the value of the current. Khalas. Thank you so much.